This presentation is about project management. Projects are fundamentally different from other things that we've talked about in the class. Most manufacturing operations, service operations, distribution centers, pretty much everything that we've talked about in the class, we hope, if we manage them or own them, will continue to go on and on. They won't terminate. On the other hand, a project is different because it has a planned end and a planned beginning, for that matter. It will exist for a finite amount of time. For most other businesses, we hope at least, that they'll go on forever. A project can be thought about as a set of individual tasks that have to happen in a particular sequence. Each one of those tasks is unique, and when each one of those tasks is done, the project is done. Most of us have been involved in projects. Certainly, I think it's safe to say everybody in the class will be involved in numerous projects in the workplace. Here's just a few examples: installing a new computer system, building a building, new product introductions, consulting engagements, audits, engineering to order and building something like a satellite, real highly complex piece of equipment that you're only going to build one of, and you're probably going to design as well, is an example of a project. Projects are not easy to manage. That's the idea of this project triad. The idea here is that there's three different deliverables that we'd like to have from any project. Those are to get it done on time, on budget, and with all specifications met. However, very often we can't get all three of these done. We can only get two. So the idea here is, I can do it on time and I can do it on budget, but chances are we're going to wind up having to cut some of the specifications, cut some of the deliverables out of the project that we had originally planned on delivering. Or we can do it on time and meet all the specifications, but guess what? It's probably not going to happen on budget. It's probably going to cost us a little bit more than we thought it was going to cost. Projects are difficult. I'm sure that we can all think in our own experience of times when construction projects or other projects did not get done when they were expected to get done. Fortunately, there are some tools and some techniques and some concepts that we'll talk about that can improve our ability to manage projects. So to break this down a little bit more formally, projects consist of activities. Some activities have to be done before other activities. So there's what we call precedence relationships in projects. On the other hand, some activities are independent of other activities. For example, if you're baking a cake, you've got to open the box, assuming you're using a mix. You've got to open the box before you can mix the cake mix and the water together. And you've got to mix the cake mix and the water together before you dump it in the pan. And you've got to dump it in the pan before you put it in the oven. So those activities have a precedence relationship. On the other hand, you can make the icing before or after you do that stuff. So the activities involved in making the icing are independent of the activities involved in making the other part of the cake. You do have to do all the activities in the project, however, and that's something that I want to emphasize because some students get confused on this sometimes. That anytime you see a project diagram, we'll talk about project diagrams here in a minute. The assumption is that all the activities have to be done. You can't, for example, just pick the cheapest activities and do the cheapest activities, or the shortest activities and do the shortest activities. You got to do all the activities. Otherwise, it's not going to be a very good cake. There's a couple different ways to represent these precedence relationships. One is with what's called PERT CPM. PERT CPM can use either activity on node diagrams or activity on arrow diagrams. In our class, we're going to use activity on node diagrams. And Gantt charts, or sort of bar charts, are another way to represent projects. The textbook uses a few Gantt charts as well, where the time it takes to do an activity is represented by a horizontal bar. So here we have an example of an activity on node diagram. So this project has a number of different activities, activity A, B, C, D, E, and so on. Again, we have to do all the activities to get the project done. And there's precedence here. Activity A is the first activity that has to be done, and the next two activities that have to be done are D and B, but neither one of those activities can start until activity A is completed. And you can see the other precedences are indicated here. I've just kind of put these fictitious names in here. So if this was a diagram for baking a cake, activity G might be mixed together the batter and the eggs, just for example. But a lot of times, just to simplify things in class, we just use letters instead of activity names. And we've also got the duration, or the time to complete each activity. So for example, for activity D, the time to complete is 5 days. For activity A, the time to complete is 3 days. So how long do you think it's going to take to complete this project? I'd advise you to pause the presentation and think about that question for just a minute. The way to answer the question is to recognize that there are 3 paths through this project. 3 sequences of of activities that have to happen in order. There's A, D, G, I, A, B, E, G, I, and then A, B, C, F. So we can add up the time it takes to do each one of those paths through the project, and the path with the longest time is going to determine, or is going to be, the path that determines how long it takes me to do the project. The amount of time it takes me to do that path is the amount of time that it's going to take me to do the project. Let's work through this, and that'll probably make a lot more sense. So the first path, A, D, G, I, it's going to take 3 plus 5 plus 3 plus 2, or 13 days. So the second path through the project is A, B, E, G, I, and that's going to take 3 plus 8 is 11, plus 4 plus 3 plus 2, or 20 days. And then the last path, A, B, C, F, is going to take, let's see, 11, 12, 14 days. So it's going to take 20 days to get this project done, assuming I don't waste a bunch of time or anything here on these other paths. Assuming I start activity D at the right time, and so on. So the shortest amount of time I can get this thing done is 20 days. This next slide just adds up those times, shows you another shot of that. So the name for that longest path through the network is the critical path. It's the critical path because it's critical. It's the path that determines the amount of time it takes us to get the project done. If an activity on the critical path gets delayed, what happens? In other words, what happens if it takes 6 days instead of 4 days to complete activity E? Well, that's going to delay completion of our project, right? So now our project's going to take 22 days. So any delay on the critical path is going to delay completion of our project. So each activity on the critical path is referred to as a critical activity. It's critical. What about these other activities? What would happen if activity C here wound up taking 3 days instead of 1 day? Would that delay completion of our project? No, it wouldn't. It would mean that this path would take 17 days, but as long as C starts as soon as B terminates, that's not going to impact the completion of our project, right? Because now this path may finish up on day 17 instead of day 14, but this path still isn't going to get done till day 20. So there's some extra time on these non-critical paths, these non-critical activities, activities C, F, and D, have some extra time on them. They can be delayed a little bit and not delay completion of the project. The name for that is slack. Slack is the amount of time that an activity can be delayed without delaying the entire project. So critical activities don't have any slack. Non-critical activities have some slack. They can be delayed, but they can't be delayed infinitely. A non-critical activity might be delayed enough that the critical path actually shifts. Going back to our project network, if activity C winds up taking 10 days, then that is going to delay the project. Right now, if we go back to our original activity time estimates, we've got 14 days to get this path done. So this path has 6 days of slack. The difference between 20, the time on our critical path, and the time for this path is 6. So far, what we've talked about in this presentation, we've assumed that the activity times for each task in the project are deterministic, that we know how much time they'll take. But you're probably saying to yourself, based on what you learned when we talked about the theory of constraints and just-in-time systems when we did our line simulations, that, hey, I know that these activity times are estimates, but most of the time the estimate's not correct. The estimate is the average, but sometimes it's going to take less time than the estimate. Sometimes it's going to take more time than the estimate. And of course that does indeed apply to projects. With projects, we have a time estimate, but there's also a certain amount of uncertainty around that estimate, and that's just like the mean or the average and the standard deviation when we looked at processing times in our constraint management simulators or our just-in-time simulators. And as you know from those situations, the fact that we have variability, that we have uncertainty, really complicates life. And it does make project management a little bit more complicated too. Let's face it, if it weren't for uncertainty, this stuff wouldn't be very much fun. So to cope with uncertainty, one useful thing in project management is to estimate for each activity a most likely time, a pessimistic time, and an optimistic time. So if you're a project manager and you're working with different resources, different departments, these are the 3 estimates that you would want to get from those folks, from the person that's responsible for each particular activity. Based on these things, we can then compute what we think is a best estimate for each activity time, and we can also compute the level of uncertainty using either the variance or the standard deviation. We can do that for each activity. Once we do it for each activity, we can do it for any path in the project. And once we figure out that stuff for the path, particularly the path standard deviation, we can then figure out the probability of completing any path in a certain amount of time. For example, what would be the probability for the project that we've looked at of actually getting it done in 20 days? Or let's say the client wants it done in 19 days. What would be the probability of getting it done in 19 days? What would be the probability of getting it done in 21 days? So we can answer those questions for any path or for the entire project. So let's talk about how we do that. Again, for each activity, we can figure out the expected time if we get an estimate of the optimistic time, the most likely time, the pessimistic time. We basically do a weighted average where we give the most likely time a weight of 4, and we give the optimistic and the pessimistic a weight of 1. So to just look at that more mathematically, you take 4 times the most likely estimate plus 1 times the optimistic estimate plus 1 times the pessimistic estimate, and you divide that by 6. So that gives you, essentially what would be kind of analogous to the mean time, the average time, the expected time. That's what we think is going to happen. And then the variance we can get by looking at the difference between the pessimistic and the optimistic, dividing that difference by 6, and then squaring that. Let's start out by just talking about the expected times, and then we'll get into the uncertainty piece. Okay, so here we've got a particular activity, activity A. This is from a different project. This is not the same project that we've been looking at. The most likely time is 4 days. The optimistic completion time is 3 days. Might be able to get it done in 3. The pessimistic time is 6 days. So to figure out the expected time, we take 4 times the most likely estimate, 4 times 4, and add to that the optimistic and the most likely. We add all that together, and again, we divide by 6, and that gives us an expected time of 4.2 days, 4.2. So here we've got a little project, just consists of 4 activities, and kind of a dummy activity here, a finish activity. So this is just basically 2 parallel paths that we have to get done. And I've got the information here for each one of the activities, the most likely time, the optimistic estimate, and the pessimistic estimate. We already computed this first one, and that was 4.2. So I'll just pencil that in there to remind us. So the question now is, 2 questions actually. What's the expected completion time for each path? And then what is the expected completion time for the project? So let's do the same analysis for activity B. So remember, we have to take 4 times the most likely estimate, and then we add to that the optimistic and the pessimistic estimate. So that would be 3 times 4, 12, plus 6 is 18. We want to divide that whole thing by 6 to get our expected time, which in this case is 3. Exactly 3. And here I've just kind of done the analysis on activity C and activity D. You can work that and make sure you get those same numbers. So the question then is, what's the expected completion time for the path? To get the expected completion time for the path, we just add together the expected completions for each activity on the path. So for the top path here, path AB, it would just be 4.2 plus 3.0. Got that here. 4.2 plus 3.0, or 7.2. So we would expect the top path to take 7.2. We do the same thing down here at the bottom, and we figure this path will take 8 days. So it's just like when we were dealing with deterministic estimates. If we want to know how long it's going to take to get the project done, well, that's the longest path through the network, or the longest path through the project. In this case, that's the bottom path. 8 days. So our expected completion time would be 8 days. Okay, but remember, we're dealing with some variability here. So it's not always going to take 8 days, right? Sometimes it might take more than 8 days. Sometimes it might take less than 8 days. So the question then becomes, what's the probability of getting any particular path done in a certain number of days? What's the probability of getting the entire project done in a particular amount of days? And let's just say in this case we're interested in what's the probability of getting this thing done in 8 days. Would it be smart for us to commit to the client or our boss or whomever to do this, get this thing done in 8 days? Well, let's begin to kind of break that down a little bit. We've got to estimate the variance. Remember, variance is just the standard deviation squared. So variance and standard deviation are basically 2 sides of the same coin, so to speak. We got to estimate the variance of each activity in order to estimate the variance of each path. And then if we can do that, we can, of course, always convert standard deviations to probabilities, so we can begin to draw some conclusions or make some predictions about the probabilities of getting things done in a certain amount of time. So let's talk about how we do that. Okay, recall from earlier, we had the formula for the activity variance. This is the variance of a particular activity, and the variance is just the difference between the pessimistic and the optimistic divided by 6, and then we square it. So to get the variance of activity A, we just take the difference between the pessimistic and the optimistic, or 6 minus 3, divide it by 6 and square it. And if you do the math on that, you'll see that turns out to 2.5. So that gives us the activity time variance. If I want to figure out the variance for the path, I just simply add together the variances for each activity on the path. So the variance for this top path would be 0.25 times 0.11, or 0.36, and the variance for the bottom path would be 0.25 times 0.25, or plus 0.25, or 0.5. Remember, the variance is an expression of the uncertainty around our estimates of getting the path done on time. So there's more uncertainty on the second path than there is on the first path. So using this information, we can start or continue to hone in on our question about what is the probability of getting a particular path done in a particular amount of time. In this case, what's the probability of getting either path done in 8 days? Let's start out by talking about path A. As we did on the previous slide here, I've just made a note that my variance for the entire path is 0.36. Remember, I can convert variance to standard deviation, and then I can convert standard deviation to probability, and that's basically what we're going to do. Here is the formula for getting the z-score here in the box. You can take a look at the formula. I'm going to try to explain this a little bit more intuitively, and then we can come back and we can look at the math on the formula. So my expected completion time, we calculated that earlier, is 7.2 days. Remember, that's just the sum of the expected completion times for each activity. So if we from an earlier slide, we want to get this thing done in 8 days. So we want to get this thing done 8/10 of a day later than our expected time. So what's the probability that we can do that? Well, remember, if we're dealing with probability, we've got to be able to convert this to standard deviations. So we want to get this thing done, we're willing to get this thing done 8/10 of a day late. How many standard deviations is that? Well, of course, we've got to ask ourselves, what is one standard deviation? Well, we know the variance. Remember, we got the variance, right? If we take the variance and we take the square root of the variance, that's going to give us the standard deviation, right? I mean, that's universal. You learned that in statistics. Standard deviation is simply the square root of the variance. So our variance is 0.36. We take the square root of that, and that gives us 0.6. So how many standard deviations is 8/10 of a day? Well, we got to take our 8/10 and divide that by one standard deviation, and that tells us that 8/10 of a day is 1.33 standard deviations, or 1.33 z-scores above the mean. So if you want to look at that a little bit more mathematically, look at the math a little bit more formally, that's what we've got here in the box. This is a formula from the textbook. So we just take the specified time, the time that we're interested in, which is 8 days, and subtract out the expected time of 7.2 days, and that gives us 0.88 of a day, and then we got to divide that by the standard deviation of the path estimate, and remember, we computed that as 0.6. So that looks like what we just did. That is exactly what we just did, and that gives us 1.33, the z-score that we're interested in. So we can simply convert 1.33 to a probability, and that'll tell us the probability of getting this particular path done in 8 days. Of course, to convert a z-score to a probability, we need to go to our normal table, and if you look up 1.33 in the margins of the normal table, you'll see that the number in the body that corresponds to that is 0.4082. So that's roughly 40.8%. that's above the mean, the area below the mean, of course, is always equal to 50%. So that means the probability is 0.408 plus zero point 0.5, or about 0.908, which is the same thing as 90.8%. So there's about a 90.8% chance of getting this particular path done in 8 days. Right? Even though 8 days is a little bit longer than the expected time, Murphy strikes, right? Things go wrong. So the chance of getting this path done in 8 days, again, are about 90.8%. So we do the exact same thing for path B, and we see that path B, the probability of getting path B done in 8 days is 50%. And that should just intuitively make sense to you, because remember, 8 days was also our expected completion time. Right? That's kind of like the average. 50% of the time you're above the average, 50% of the time you're below the average. So about half the time, assuming the distribution is symmetrical, you're going to get this thing done on time, or this path done on time, to be a little bit more precise. Okay, so the thing that we're really interested in, of course, is what's the probability of getting the project done on time. And of course, to get the project done on time, you got to get both paths done on time. So what's the probability of making that happen? Well, if you've got a situation where the paths are independent, in other words, the paths don't cross, which is the situation that we've got in this particular project, then the probability of getting both the paths done is the product of the individual path probabilities. If that's not the case, in other words, if the paths are not independent, if the paths cross, then really the only way to answer the question is to simulate the project on a computer. We've done a little bit of simulation in this class. You've seen that simulation is a good way to kind of deal with variability. And again, that's the only way that you can answer the question if you've got paths that are not independent in the project. But fortunately, in this situation, our paths are independent. We've just got two parallel paths that we've got to get done, so we can figure out what the probability of getting the project done in a particular amount of time is. Of course, in our situation, we're interested in the probability of getting it done in 8 days. We figured out the probability of getting each path done in 8 days, right, from our previous analysis. So again, like I said in the previous slide, we just multiply the two together. 0.908 times 0.5 is about 0.458, or about 0.454, or about 45.4%. So our chances of getting the entire project done are only about 45%. And that really, what's driving that is this very low probability of getting CD done on time. So I think this is a really important thing to understand, is this idea of multiplicative probabilities. Let's say we had 4 or 5 different paths coming together. Even if each one of those had a 95% chance of getting done on time, let's say we had 5 paths coming together and each one had a 95% chance of getting done on time, then our chances of getting the entire project done would only be 0.95 to the 5th power. And if you do that on your calculator, if you multiply 0.95 times 0.95 times 0.95 times 0.95, or just simply take 0.95 to the 5th, you'll see that's only a 77% chance of getting done, right? And a lot of times in projects, that's the situation. You have a lot of things coming together that need to get done. The chances of getting any one of those things done is pretty high, but when you put them all together, it only takes one, basically, to make the whole project late.